Okay, so I'm Chaya Stern. I'm a graduate student at the Tri-Institutional Program in Chemical Biology at Sloan Kettering and Weill Cornell at the East Side. So I study computational chemistry. Particularly, I'll be talking about how I use Bayesian inference in computational chemistry, but particular how I use it to fit molecular models that are models that describe the inter and intramolecular forces of atoms. And these models are important when studying the dynamics of proteins or other macromolecules. And they're also really important in drug discovery, which will be the focus, that utility is the focus of what I'm developing this for. So just a little outline what I'll be talking about. So first I'll discuss how these models are used in drug discovery. And then I'll talk about Bayesian inference of the model parameters and model selection, and how I did that with Pymc. And then I'll briefly, I don't think there'll be too much time for this, but I'll briefly touch upon reweighting and error propagation using the posterior. Okay, so biological macromolecules are the molecular machines of life, and they're involved in many different functions such as structural, signaling, transport, catalysts, regulations, biosynthesis. When there are perturbations in these molecules, that can lead to a disease state, and small molecules can be used to mitigate the disease state by interacting with a protein, either turning it on or off. There are other ways to do therapeutics, but this is one canonical way that small molecules interact with proteins in disease states. However, while there are many success stories of drug discovery, many of them usually end in failure. So this graph, the y-axis here shows the number of drugs that were developed using per billion US dollars over the years. And as you can clearly see, this process has been becoming increasingly inefficient. The current estimate, it has been estimated that the cost of developing a new drug doubles every 9 years. And the current estimate of the drug development process is $2.6 billion per drug. This includes all the failures, but it's still an astronomical amount to get a new drug on the market. And even when you look at the drugs that do get onto the market, most of them are not really innovative. They're just changing some of the chemicals of the chemical moieties on the drugs for patent purposes. So it has actually gotten so bad that this was named Eroom's law to contrast Moore's law, which describes the exponential growth of transistor technology. So we believe that the drug discovery process has the preclinical phase and the clinical phase, and this process has a 92% failure rate. So we believe that intervening early on in the drug discovery process with these computational molecular models can increase the efficiency of the initial stage and also ensure that drugs that will fail do not enter the more expensive phase of the drug discovery process. So what do these models look like? So in molecular mechanics simulations, which is the models that we're using, the inter and intramolecular forces are modeled with what we call a force field. The force field is a Newtonian approximation of the underlying quantum mechanics. So the reason why we don't do quantum mechanics, which would actually be the true description of the system, is because it's just way too computationally expensive. So we need to use approximations. So these models, in these models, the atoms are modeled as point masses with a fixed charge, and the vibrations of the molecule, such as the bond vibration, the angle vibration, are modeled as harmonic oscillators, as a spring, and there's a K, which is the force constant that controls the vibration, and there's an equilibrium length. And so besides this bond term, there are many other terms such as angles, non-bonded, the energy of the rotation of the molecule around the central bond. So the terms, these functional forms in this model have free parameters that need to be fit to reproduce experimental data. And then, once you have this model parameterized, you can run a simulation. And in this case, we have what I'm showing here is alpranolol, which is a drug used to treat hypertension. And you see it found its binding site in the binding pocket of its target protein, and it binds to it. This movie was generated using molecular dynamics, which is one kind of simulation. It was generated by the people at, well, not D. Shaw, but Desres, which is also David Shaw's company. It's a computational chemistry company, and this was generated on their supercomputer that they built that has specialized hardware to run these kinds of simulations. So these simulations provide us access to atomic level detail of how the drug interacts with proteins. However, this is more of a qualitative understanding of what's going on, and what we're really after is a quantitative prediction of properties of molecules that we can use to predict which, if we want to design a new molecule, we can predict which molecule will better bind to its target protein. So how would this be used in a drug discovery process? Say you're a medicinal chemist and you found some molecule, some scaffold, some chemical scaffold that seems to be binding to a protein. You want to do some chemical transformation to optimize the binding. So there's a combinatorial amount of chemical transformations that you can do. And so before you do that, you can go over to the computational chemist, or if the tools are available, you can run these calculations on your own and calculate the relative binding energy that describes how well this molecule will bind to the protein. And then you get a ranking of some better binders, worse binders. However, if you don't have the uncertainty of these rankings, you can assume that the top-ranked drug will bind best to the protein. However, when you do add the uncertainty on top of that, you can see that some of them might be coming from the same distribution, so it's not actually a better binder. And as a computational chemist, you don't get that many chances with a medicinal chemist with making predictions before they lose trust if those predictions don't actually pan out. So it's crucial to understand what the uncertainty in these predictions are. And there are many reasons why these computations fail. There are many sources of error that contribute to the uncertainty. So the first is the force field, which is our model, which does a poor job of describing the physics of the system. We also might be missing essential chemicals or essential chemistry and physics when we set up our system that is not well described. Or another big issue we have is a sampling problem, because the distributions we're trying to sample are very complex, highly dimensional, with many narrow wells. So if we don't sample the distribution well enough, then we will not be able to make good predictions. So several of my colleagues in our lab are working on other aspects of this problem. The problem that I'm working on is the force field problem, and trying to parameterize these force fields such that they represent the chemistry and the physics. And in addition, we currently don't know how much uncertainty these models contribute to our predictions. So what I also want to do is quantify the uncertainty that these models, the model parameters, introduce to our predictions. So how are force fields currently made? Many graduate students and postdocs have given a lot of time for this, and it's a lot of work in trying to. Data generation is hard, getting the right data, and then trying to fit these models to reproduce experimental data that's condensed phase, and then we get some parameter set that we hope someone uses, we hope is accurate. So can a Bayesian approach provide a better way to fit force fields? So what we do is we cast the parameterization of the force field as a Bayesian inference problem. So we use Bayes rules, and that provides a probability measure over the unknown parameters given the data. So what we have is we have some either experimental data or quantum mechanics data. We have uncertainty and errors associated with this data, and we set up an error model as our likelihood, and then we add some priors onto our parameters. And then we can use MCMC or several other MCMC type algorithms that the physical chemistry community is very familiar with to sample the posterior. And then what we get are multiple parameter sets that are consistent with the data. So this Bayesian approach provides us a very straightforward way to propagate the uncertainty to the computed properties. So first we compute the property that we're trying to estimate with some representative parameter set, and in my case, I usually end up using the map estimate for that. And then, I mean, normally you would recalculate this value with the other parameters of the parameter set. However, in our case, to get an estimate of this value is very expensive because you have to run a molecular simulation. So we use reweighting techniques to estimate this value, and then we get a distribution of that value, and the width describes the uncertainty. The width of this distribution describes the uncertainty of the computed property that's coming from the parameters. Okay, so the term that I'm going to be talking about is the dihedral energy. So the dihedral energy is the energy of the molecule as it rotates around its central bond. So this is just a simple molecule of butane. It's just a GIF of the molecule rotating around the central bond. So as these parts of the molecule come closer together, there's a spike in energy because of the repulsive forces. And then as they move further apart, this would be a low energy state of the molecule. So you can use quantum mechanics to calculate the energy of this molecule at different dihedral angles, which is the angles formed by the plane formed by these three atoms and those three atoms. And you get this curve. This is just showing the QM energy and the MM energy of this curve. And this curve, okay, and these are just in chemistry, this is called the Fisher projection of the orientation of the molecule. So it's just a easier way to look at the configuration of the molecule. So this is usually in most force field given as a Fourier series. So what I'm trying to do is fit the k's and the n's of this Fourier series such that it reproduces the dihedral energy, the quantum mechanics dihedral energy. I mean, the reason why I'm focusing on this part of the force field is beyond the scope of this talk, but I can talk about afterwards why I'm working on this. So the model, so I wrote this package called TorsionFit. TorsionFit, it does a lot of things besides fitting the model. It tries to automate the generation of the data and then the reweighting, but what I'll be talking about is the sampling and how I've used Pymc, and how I've used Pymc for this. So my likelihood is given as it's a normal likelihood, and the EIQM is the QM energy for the configuration I, which is the data that I'm fitting to. The EIMM is the molecular mechanics energy without the dihedral configuration. And then for the E dihedral is this function that I had shown you previously. The M is the torsion types, because there's, the torsions are described differently depending on the chemical environment of the molecule. The N is the periodicity, which describes how many minimas the curve should have, and phi is the torsion angle of the ith torsion. So I'm not. Oops. Okay. So the code is available. It's warning that it's pre-alpha, so there's still a lot of changes that are going to happen, and it's not really. I mean, you can use it, but use it at your own risk. It's not fully tested. So currently, I'm not going to show the code for this because it's currently still in Pymc 2. But it's still useful to see how this works. So what I do have, if you go to the GitHub repo that I had linked, there is there is an IPython notebook. Oops, let's get that. Can't really see what I'm doing. Oops. I should probably mirror this because this is going to be, okay. So there's the IPython notebook. That first, this just describes a lot of the background that I spoke about. And what I'm importing, of course, is matplotlib for plotting. I'm importing the MCMC model class from Pymc2. I'm also importing Seaborn for the plotting afterwards. So in order to get this to work, you also need PyMed, which is a computational chemistry library that allows seamless conversion between file formats, because that's a big problem too. And then the torsion fit, I import the toy model, which is this toy model that I had written for debugging and prototyping, but now it's a really nice toy to play with. So you instantiate this toy model, and I mean, the n increments is just how many data points you want. I'm not sampling the phase, and then I give it some true value that I will try to recapitulate. So this toy model generates synthetic data. It's not quantum mechanics data because that would be too computationally expensive. So it generates synthetic data, and here is just showing you, and here is just writing out like the random initial value that these parameters have after it was instantiated by Pymc. And then I just give the Pymc MCMC model class the Pymc parameters. That's an attribute to this toy model. And for the backend, I am actually using SQLite Plus, where I just added some extra functionality to the SQLite backend from Pymc. I'm not going to go through the sampling because it's a little slow. The reason why it's slow is because it's Pymc2. And also, it's an older model that I had written, which the current model is still using Pymc2, but it's 2 orders of magnitude faster. So this is just a little slow, but it shows it makes the point. So first, after we finish sampling, we want to look at the posterior predictive to assess the parameter fit. That's usually the first thing I look at, is how well can I recapitulate my deterministic. How well can I recapitulate the data that I'm trying to fit? So, okay, here I guess I should just go through this. So the reason why I do this here is that I get fonts, that my font for my labels are big because I can't read from far. So, so I usually just do that. Yeah, if you just want to have a look, I use the MPL RC params, the font size, and I changed that. All right, so as you can see, it gives a pretty good fit. The black is the true value, and the blue is using Seaborn. This is using like the last few hundred iterations of the MCMC chain. Okay. Now, I haven't spoken about this yet, but I'll speak about it right afterwards. I also do model selection with Pymc. So why I need model selection here is that I have, I'm trying to fit this Fourier series, right? And I want to know which multiplicity term do I need? And that's a model selection problem. So, I look at the, if I look at the output of this, I'm looking at the marginal posterior of the models, and I have 6 models that I can have. I can have 1, 2, 3, 4, 5, and 6. And if you remember, our true model was a 3, and turns out that one has a high probability. So it does model selection. And the last thing, well, there are many other things to look at, but another thing I look at is what the marginal posterior of my parameters look like, and I do recapitulate the right value. It's 20 kilojoules for the K of 3. The other ones are either 0 or they're not here because of those terms are not in the likelihood. Okay, so now that we're through this. Okay, model selection in Pymc. So why do we need to do model selection here? We want to know how many Fourier terms do we need to represent this potential energy scan. So current tools to fit these force fields rely on chemical intuition to choose the terms. And there are some physical rules that you can use to decide which terms you're going to use, but it's extremely difficult. Again, it grows exponentially, and there are many other convoluting factors that make it not a straightforward problem to just choose based on physical intuition. So how many torsion terms, how many terms will I have per torsion? So usually the Fourier series, we truncate it at n equals 6. And the reason why we truncate at n equals 6, as I said, n determines how many minimas you have. And the geometry of the molecules that we work with usually do not have more than 6 minimas. So that's why we truncate it at 6. But that still leaves us with 64 possible combination of terms. So we have to select over 64 models. And this is only per torsion, and there are many torsions in the molecule. So now, Pymc, meanwhile, does not do transdimensional, doesn't take transdimensional steps, right? So this is more of a hack that I did, but currently it's working. So I mean, bear with me a little bit as I take you through this, because this can sometimes throw some people off. So the algorithm that I use is I introduce a bit string, and the bit string represents the model. So say my bit string is 1. Right? In the bit string representation, you have a 1 where it's black and zeros where it's white. So what this would mean is that when I evaluate the likelihood, I only evaluate the n equals 1 term. And say my bit string is here. In that case, I would evaluate 1, 2, and 6, and I wouldn't evaluate the others. And I define this as a discrete uniform distribution. And then I use a bit mask in the likelihood to evaluate the right terms. So it works, but I ran into a problem where, okay, I call this reversible jump Monte Carlo, which it is reversible jump, just a different implementation of it. But then when I looked at the deviance, which tells you how good the fit is, because it looks at the negative 2 log of the likelihood. So when I use reversible jump, as you can see, it gets stuck in these metastable states. It doesn't mix well between the different models. And these states are basically different models from the discrete uniform bit string. When I use the model of 63, which allows all terms to be on, I get a much better fit. Now it's much better also because of overfitting, but that's not what I want to focus on. I want to focus on how well this mix. This does mix better. And this had baffled me, actually. I was trying to figure out why this is the case. So what I realized was that so first what I'm showing here is so what I'm showing here are 25 separate runs. And in the top right graph, I'm showing the traces of the bit strings for each run, okay? And as you can see, they start out anywhere, and then they all settle into these like 3 different metastable states and don't really mix. And the reason why this was happening is because if you think about how this was set up, you have your K's all have some prior, and I had given it an uninformative prior, and the prior was a uniform prior. But when I had a different, when that term is off, the K is now sampling the prior. Right? It's not coupled to the likelihood. So it's sampling the prior. When it's sampling the prior, the probability of it being close to the true value of K is very low. So now when I sample a new bit string that has that term on, it turns on, but the K is so far off that it affects the likelihood so strongly that it usually leads to a rejection. So it has a very high rejection rate. Or very low acceptance rate. So I was thinking, how about I change my prior, and I make my prior more biased towards 0, such that if it's closer to 0, when it's decoupled from the likelihood, it will sample values that are close to 0. And when I turn it back on, the value will be low enough, even though it's not close to the true value, it's low enough that it doesn't affect the likelihood that much, so the acceptance rate will go up, and this will lead to better mixing. And turns out that that's what happened. So what I used was a Gaussian prior with a mu of 0. And as you can see, the mixing is really good. And I mean, you see how even for the deviants, they're all good. There's the one straggler here, which for some reason gets into some metastable state. And it's stochastic, so It will happen at some point. And I believe this happened because of really bad starting conditions. It gets into these two states, which are the two correct states for this specific molecule that I was working with. I was working with butane. And the reason why there are two here is because there's some degeneracy in the model. There is some symmetry in the model, which is, again, beyond. We can discuss it afterwards. OK, so now I will touch briefly on propagating the error. So the property that I've been calculating to propagate the uncertainty is hydration-free energy. Hydration-free energy is the energy it takes to remove a molecule from water. And the reason why I use this property is it's very closely related to the binding free energy. And also it's very, at this point, it's very straightforward for us to calculate it. And it has also become a benchmark against which to test these models against, because we have the data and we know how to calculate it. And basically what it is, it's when we calculate the delta G, what we're calculating is the ratio of normalizing constants between the molecule in water versus the molecule outside of water. And instead of running many of these calculations, I ran one calculation and then used exponential averaging to reweight into the other force field parameter models. And in exponential averaging, what you do is you calculate your observable and you take into consideration the difference between the two distributions. So for a simple molecule like butane, I look at the delta G, which is the error in this delta G from the force fields. And what I find is actually very small. It's a lot smaller than the experimental error, which is around 4.2 kilojoules per mole. But when I look at a more complex molecule, which is this molecule here, I end up with a much larger error. It's in the tens of kilojoules per mole. And this is actually significant. And this will significantly impact your predictions that you're making. And this is only in hydration energies. So when you do binding energies, if it's tens of kcal for hydration-free energy, which is easier for us to calculate, it's probably higher for binding energies. Now, this led me to think about why are these errors so large? And this is still an open question, so I don't necessarily have the answers for this. But why are the errors so large? So first of all, we're using quantum mechanics data. Is that the right kind of data for us to use? And the reason, it's the one that's easily accessible to us because we can just calculate on a computer. You don't need a lab to do the experiment. But on the other hand, these quantum mechanics calculation, we're doing them in gas phase, and we're trying to simulate in liquid phase, in condensed phase. So how well does that transfer? And I'm not sure. That might be a contributing factor, or it might not. And another question is the functional forms that we're using in the force field, do they represent our systems accurately, adequately? So these are still open questions that we're thinking about. So I'll leave you with that, and I want to thank my advisor. I want to thank my program and the NSF for funding, and I'm open to questions. Yeah.
So when you have those things ordered by how likely they are to bind, and you kind of put the uncertainty around those, how do people actually translate those uncertainties into maybe what medical experiments to run next, or what to bother the medical chemists about?
That's a good question. And what we try to do is we try to give the medicinal chemist a good understanding of how good these predictions are. So many times the medicinal chemists will go and say, well, I know that these transformations maybe are not that great, but they're very easy for me to make, so I'll just make it and test it. That can help with our models. I think the point where it's very important for us to be really, really confident about the predictions when the chemical transformation is very difficult to do. So when you have to do scaffold hopping, where the entire base of the chemistry is different, so you almost have to change the molecule that you're using, then we need to be very confident. So that is where, if if we see that we have that our calculations are showing that one is really better than the others, then we try to use that to communicate that it's worth doing that change. But again, you have to be able to communicate how certain you are, because you don't want the medicinal chemist to do a lot of hard work and then come back and say, actually, well, you know, it wasn't that much better. Does that answer your question? Yeah.
In the ground view slide, you showed, talked about how grad students' parameters were just kind of thrown away. So I was wondering if there were opportunities to use those parameter estimates from the literature as like priors to kind of inform the model.
Yeah, so I definitely do that. I use that as my initial starting point. There are some people that are looking at like other parts of the force field that are constraining their priors on those values. So I mean, we try to use what's out in the literature to inform what we're doing.
Presumably, Pymc calculates gradients in the continuous parameters. Use that pit mask to introduce discrete parameters to mixed models. Did you have to turn off the gradient calculation?
Okay, so I've been using Pymc2 where I'm not using the gradient. In Pymc3, which I mean, I do want to talk to you guys afterwards. I mean, I would like to use the gradient, and I actually have an analytic form of the gradient here. So I don't necessarily need to use the Theano gradient, and also my deterministic is a little more complicated than just what's you know. I need to so I need to see about that. And you're right about it introduces a discrete variable, which creates some problems. There is another way that you can do the model selection. It's still going to be discrete, but it might be better than using a bit string, and that's using Bernoulli variables. So I can go back to that, and I can explain why. So in this case, we have these bit strings, right? And when we're proposing a new move, we try to propose a move that's close to the previous move, right? But the problem is this is an integer space. So what that means is that, let's say, model 7 is very, very different than model 8, right? So while it will propose something from 7 to 8, it will probably be rejected because the model is so different. But when you use 6 Bernoulli variables, you're only switching one at a time. So that might be a better way to do it, but that's still a discrete variable, and that still wouldn't answer your question. So, yes.
Have you considered combining just multiple force fields, whether it's like amber or charm, together, and then trying to predict like hyperparameters for multiple models?
No, I haven't tried that, and we haven't really thought about that.
Because if there's still arguments of like whose models.
Well, the problem is that they have very different philosophies in how they parameterize and what they're parameterizing to. So you
can settle the score on that for that.
Yeah, that's an interesting question. All right. Okay, thank you.